Today, we're going to finish up our work on finding the volume of solids of revolution by using the disks and washers method. So we're going to start with this problem here where we've got the region bounded by y equals 3 root x over 4 and the x-axis and then the line x equals 4. We're going to take that region and we're going to revolve it around the line x equals 4. So we're going to get something that looks kind of like this when we revolve it around. And we can see that because the region that we are revolving, this region right here, the region that we're revolving around the line x equals 4 is fully pushed up against that line, and everywhere along that line in the region, that region is fully pushed up against it, we end up with disk cross sections. So but we will note that these would need to be sliced horizontally, so this will all needing to be done in terms of y. So we're going to do pi times an integral from the lowest y value in this region, which is 0, to the highest y value in this region, which we can see from the graph that's 3, but if it wasn't completely evident, we could just plug x equals 4 into our equation. 3 times the square root of 4 over 4 is just 3. So we're going to integrate from 0 to 3, the radius squared. And so our radius of any of these slices extends from the function over to the line x equals 4. So what we'll need to do is we'll need to make a note that this section, this little piece here in this case, from the y-axis to x equals, or from the y-axis to function is x. And then we know that from the y-axis to the line x equals 4 is 4. So our radius is going to be that full distance from the y-axis to x equals 4, that distance of 4, minus the little x value that we've got that reaches from the y-axis to the function. So our radius is 4 minus x, but we can't put 4 minus x squared in here because this problem needs to be done in terms of y. So what we'll do instead is we'll take our original function, y equals 3 root x over 4, and we'll just divide by 3. So we'll get y over 3 is equal to root x over 4. We'll square both sides to get y squared over 9 is equal to x over 4. And we'll get that x in terms of y is equal to 4y squared over 9. So our radius should be 4 minus 4y squared over 9. And then we'll square that. And for quite a few of the integrals that we're going to work through today, we're not going to bother to actually integrate them and evaluate them. Now, this is a pretty straightforward integral. You should just distribute out the inside of this, and then you'll just use the power rule to integrate it. So you need to know how to do that, but our main point here, since we've already had a couple of units here on integration, where you should be able to integrate those, our main point here is how do you set up these integrals? So that's mostly what we're going to be focusing on for the rest of this unit. It's just getting the integrals set up. So for this next one, we've got the region between the x-axis and y equals the natural log of x. Let me sketch y equals the natural log of x. And then we've got the line x equals e. And like I said, the x-axis. So we're talking about this region right here. Okay. And we're going to revolve that region around the y-axis. So if we were to do that, we'd end up with something over here that looks kind of like this. And we'll note that the cross sections are going to end up being washers because the region we're revolving is not fully pushed up against. In fact, it's not touching the y-axis even at all. So we're going to have an outer radius and an inner radius, and everything's going to need to be done in terms of y. So we're going to have pi. We're going to have an outer radius squared and an inner radius squared, and dy. And then we're going to integrate from the lowest bound of this region, which is y equals 0, down there on the x-axis, up to the highest y value in this region, which we can see here that if x is e, y is equal to the natural log of e, which is just 1. So the highest bound of our region is 1. And then we need to find our outer radius, capital R, and our inner radius. Well, our outer radius extends, when we're doing this in terms of y, from the line you're revolving around, so from the from the y-axis, from our y-axis here, all the way over to the right bound of our region. That's capital R, a big radius. And that is from one vertical line to another. So it's just that horizontal distance of E. And then our inner radius, which should extend from the line we're revolving around to the left bound of the region, should be that entire distance that we just saw, that full outer radius. Actually, it should just be the distance from the y-axis to the function. Right? The distance from the y-axis to a function is always just x. But in this case, since we're doing it in terms of y, we need to turn x into terms of y. So we'll exponentiate both sides of this to get e to the y is equal to x. And so our inner radius is e to the y. So here we've got e squared, outer radius squared, minus e to the y squared, and then dy. And just for the fun of it, we will evaluate this one for a couple of reasons, just to remind ourselves about how some of these things work. We've got pi times an integral from 0 to 1 of e squared minus e to the 2y dy, because e to the y squared, you just multiply the exponents. And now when we integrate e squared, we'll remember that e squared is just a constant. So if you integrate a constant, dy, you get the constant times y. We have pi times e squared y minus the integral of e to the 2y. So that's one of the ones that you should be able to do in your head by now with the basic u sub. But remember that e to the 2y, we would let u equal 2y, where du would be 2 dy. So in order to get that, we'd have to put in a 2 and a 1/2. Right? And that 2 goes away with the dy to become a du. So we'd really end up with 1/2 the integral of e to the u du. And we know that the integral of e to the u is e to the u. So we'd end up with 1/2 e to the 2y. So evaluating that from 0 to 1. And so now we've just got pi times e squared minus 1/2 e squared when you plug in 1, minus, and be careful that you actually plug the 0 in. A lot of people just say, oh, the lower limit is 0, so the value of this thing is 0. Well, that's not necessarily true. E squared times 0 is 0, but minus 1/2 e to the 0 is minus 1/2. And so our final answer here is pi times 1/2 e squared, because e squared minus 1/2 e squared, be a half e squared, and minus a negative half or plus 1/2. So for this next one, we're going to get used to looking at this region right here. What we're going to do is something that's most likely going to happen on the test that you're going to see for this unit, is I'm going to give you a region. In this case, the region between y equals 4 over x, y equals 0, so the x-axis, then x equals 2 and x equals 4. And we're going to revolve it around, in this case, around the x-axis. But we're also going to set up integrals to do this around a bunch of other horizontal lines and a bunch of vertical lines. So we'll start with trying to revolve it around just the x-axis, which should be really pretty straightforward. We're going to revolve this region around the x-axis. We're going to get something that looks about like that. And we just want to slice this thing vertically. So we get dx. So everything's going to be done in terms of x here. And it should just be pi times an integral from the left bound 2 to the right bound 4 of our radius. And our radius here is just the distance from the x-axis to our function, which is y. So that radius is just, in terms of x, 4 over x. So we end up with pi times the integral from 2 to 4 of quantity 4 over x squared dx. We'll call that good right there. That's the setup. If we wanted to actually integrate that, you can just square the 4 over x, get 16 over x squared, and use the power rule. So here we've got the same region, but this time we're going to revolve around the line y equals -2. We're going to revolve around this line down here. And so now, even though it's the same region, now that region is not fully pushed up against the line that we're revolving it around. So this time, we're going to end up having to do washer cross sections. Right? As I revolve this around this line, I'm going to have kind of a thing down here. And in the middle, I'm going to have a gap. I'm going to have a washer cross section. So we're still going to need to do this in terms of x, and it's still going to be pi, and it's still going to be an integral from 2 to 4. But now we're going to have an outer radius squared and an inner radius squared. And then we'll have our dx down at the end. So our outer radius is just going to extend from the line that we're revolving around down to, or up to, the function itself. So the distance from the function itself to the x-axis is y, or 4 over x. And the bottom distance here from y equals -2, y equals -2, up to the x-axis is 2. And so our outer radius is 2 plus 4 over x. And then we'll square that. And then our inner radius is just the distance from the lower bound of our region to the line we're revolving around. And that's just this 2 units down there on the bottom. So -2 squared dx. And that's our setup. Of course, we could distribute 2 plus 4 over x times 2 plus 4 over x, and then subtract 4 from it at the end, and then we'd integrate using the power rule. But that's a pretty straightforward integral. And again, our focus for today is just being able to properly set up the integrals. So here we're looking at the exact same region, but now we're going to revolve around a horizontal line y equals 6 that's way above the region. So as we do this, again, we should be able to see very clearly that this is just going to be washer cross sections again. And we could sketch what the solid looks like if we want to, but I think having done so many of these now, we should be able to kind of figure out what it is without sketching that actual solid. We know that the washer cross sections mean that we're going to do pi times an integral from 2 to 4, again, the left x value to the right x value. And we know we're going to have an outer radius. And so our outer radius should just be extending from the line we're revolving around all the way down to the lower bound of the region. That outer radius should just be 6 units. So we're going to do 6 squared minus our inner radius. And our inner radius is going to extend from the line we're revolving around to the upper bound of our region. And so we have to take into account that this little bottom piece here is y, which is 4 over x. So our inner radius ought to be the full distance of 6 minus y, or 6 minus 4 over x. So our inner radius is going to be 6 minus 4 over x. We'll square that, and it gets a dx. And again, we could distribute that out, and then integrate using the power rule and evaluate it. But this is going to be good enough as our setup. And for a lot of the problems in the free response on the AP test, especially on the area and volume FRQs, they'll often just ask you to set up and not evaluate some of the integrals. And so this would be a perfectly acceptable answer for some of the area and volume FRQs on these. So for this next one, we're now, instead of revolving this around a horizontal line, we're going to revolve it around the y-axis. So we're going to revolve it around a vertical line here. And we'll first note that the region that we're talking about is not fully pushed up against this line. In fact, it's not even touching it at all, which means that over here, we're going to get some cross sections. I know that doesn't look very good, but I just kind of run out of room there. We're going to get some cross sections that look like washers. And we're going to have to slice this thing horizontally so that we're stacking up an infinite number of these little washer cross sections, which means we're going to be doing this all in terms of y. And we're going to have to find an outer radius and an inner radius, and we're going to have to do even a little extra work here, because what we'll note for this one that's going to complicate things a bit is that if we look at our region from y equals 0 to y equals 1, and we can see that when x is 4, we get a y value of 1. The right bound of our region is the line x equals 4, and the left bound is the line x equals 2. But from y equals 1 up to y equals 2, the right bound of our region is the function, whereas the left bound of our region is still that line x equals 2. We have a switch in what the right bound of our region is, which means that if we're doing this in terms of y, we're going to have to separate this into two different integrals. One that's going to go from 0 to 1, and another that's going to go from 1 to 2, because we have two different values that will make up our outer radius. So from 0 to 1, our outer radius is just the distance from the line we're revolving around to that right bound of x equals 4. It's just 4 units. So our first integral is going to be 4 squared minus the inner radius, which is just going to be the distance from 0 to 2. So 4 squared minus 2 squared. When we do our second integral, our outer radius, though, extends from the y-axis over to the function, which is a distance of x. Right? And x, if we go in here and solve this for x, we get x is equal to 4 over y. So for this one, our outer radius is just going to be 4 over y, and we'll have to square that. And our inner radius doesn't change. The inner radius is still that line x equals, the distance from x equals 0 to x equals 2. So that'll still be minus 2 squared. And so because that right bound of our region changes, we have to separate this into two different integrals. Same would be true if our left bound of our region changed. And this would be an acceptable answer if this was a problem that said not to evaluate it. And of course, any of this could be evaluated easily enough by just simplifying the integrands down and then using the power. So let's see what happens when we revolve this around the line x equals 2. So when we go around this line x equals 2 right here, we can see that our region that we're talking about is fully pushed up against that axis. So as we revolve that around, we're just going to get some nice disk cross sections that are going to be done in terms of y. But because that we still have that same issue where the right-hand bound of our region is the line x equals 4, and then it changes to being the function y equals 4 over x, we're going to have to still separate this out into two different integrals. So for the first one, we're going to have pi times an integral from 0 to 1. So we're talking about this first section where the right bound of the region is the line x equals 4. Our radius is just going to be the units, the 2 units from x equals 2 to x equals 4. So it'll be pi times the integral from 0 to 1 of 2 squared dy. And then we'll add to that pi times the integral from 1 to 2 of this distance, the distance from x equals 2 to the function. And you might be tempted to call that a distance of x, but we have to remember that x is always measured from the y-axis all the way over to the function. So this whole distance here is x, but our radius, this value right here, is actually equal to that full x that we just talked about minus the distance of 2. And we know that the value of x from working on the previous problem was just 4 over y. So our radius here is going to be 4 over y minus 2. So we'll throw that in our integral up here. 4 over y minus 2 squared dy. So again, we got from 0 to 1, our radius is just 2 units there. But from 1 to 2, our radius being just this little piece, the distance from 2 to the function, that would be full x minus the 2. And again, we could simplify that and use the power rule to evaluate it, but this ought to be good enough for us for today. So we're going to do this again. This time we're going to revolve it around the line x equals 4. So now we're going around this line right here. And again, we're still talking about the exact same region. But for this one, we'll notice that our region is not fully pushed up against the axis that we're revolving it around. Right? And so as we need to think about this, we're going to have to think about it being washer cross sections for a portion of it. If we remember, right, we were talking about the right bound of our region changes. So for part of this, from 0 to 1, we don't have washer cross sections, right? We actually have disk cross sections there, right? Because for part of this section, from 0 to 1 here, it is fully pushed up against. And so that radius along this rectangular portion of it, that radius is just going to be 2. So this will just be 2 squared dy. And then we're going to add to that pi times the integral from 1 to 2. But this time, because we do have this gap in the middle here, right, we're revolving the upper piece of it here around. We do have a gap. And so our outer radius is still the distance from 2 to 4, which is 2 units, so 2 squared. But now we have to subtract from that our inner radius, right? And our inner radius is the distance from the function over to the line that we're revolving around. Well, this entire distance right here is just going to be 4 units, but we need to knock off x units from that to give us this inner radius. So our inner radius for the upper piece is just 4 minus x, which we know is 4 minus 4 over y. So we've got pi times the integral from 1 to 2 of 2 squared minus 4 over y squared dy. And for this one, we're going to revolve around the line x equals -2. So if we're going to go around x equals -2 over here, I think quite obviously our region that we're revolving is not pushed up against this, not even at all. And we know we're going to have to do two separate integrals because this is still going to be done in terms of y. So we're going to have pi times an integral from 0 to 1 of our outer radius. And so our outer radius from 0 to 1 extends from this line all the way over to the line x equals 4. That's the right bound of the region. So from -2 to 4 is 6 units, so 6 squared. And then minus our inner radius, which extends from that same line over to x equals 2, the left bound of our region, which is 4 units. So 6 squared minus 4 squared dy. And then we'll add to that pi times the integral from 1 to 2 of our outer radius. Well, if we're extending over to this right here, to our function, right, from x equals -2, a portion of that is 2 units, and the other portion of that is x. So that outer radius is going to be 2 plus x, or 2 plus 4 over y. So the start of this one should be 2 plus 4 over y squared. And then we'll subtract from that the inner radius. And our inner radius is just going to extend from x equals -2 over to x equals 2, which is 4 units. So -4 squared, and then dy. And so we'll do one last one of these. This time we're going to revolve it around the line x equals 6. So we'll have revolved this region around the x-axis and then around a line that's above and a line that's below that. We'll have then revolved it around the y-axis. We'll have revolved it around both the left and the right bounds of it, x equals 2 and x equals 4, plus a line further to the left of it and another line now to the right of this region. So in order to figure out what this is going to look like, we know we're still going to do pi times an integral from 0 to 1 of our outer radius and our inner radius. And so in this case, our outer radius is going to extend from x equals 2 to x equals 6, so 4 units. And our inner radius from 0 to 1 is just going to go from 4 to 6. So that ought to be 2 squared dy. And then we'll add to it pi times the integral from 1 to 2. And from 1 to 2, the outer radius is still going to be the same value. Right? We're still going to extend from 2 to 6 there. So that'll be 4 squared. But then we'll subtract from that our inner radius. And our inner radius is this distance from the function to x equals 6. And since we know that from the function to the x-axis is x, and the whole distance here is 6, this inner radius ought to be 6 minus x. And since we know that x is 4 over y, our inner radius should be 6 minus 4 over y. And then we'll square that, add our dy in. And again, all of these integrals that we've done here today with this region, we could have simplified all these down, just simplify the integrands, and then they all just required power rule, or a couple of them here would have required some natural logs in them, but pretty straightforward integrals to take care of if we need to. So that's the end of our discussion about finding the volume of solids of revolution using disks and washers. And next time we'll have our last lesson of new material for the school year, where we talk about finding the volume of solids of revolution in another method, which we call cylindrical shells. So that'll be next time, and that's it for today.